Yeah, today we are going to look into the photochemistry of carbonyl compounds, photoaddition of carbonyl compounds to alkene. Last few terms we have been discussing about initially what we have mentioned that the carbonyl compounds in basically undergo 4 different types of reaction: Norris type 1 reaction, Norris type 2 reaction. These two reactions are very common in aliphatic carbene compounds and also in alicyclic carbene compounds. So for last few terms we have been discussing about these two types of reaction. Last time we have also discussed about the photoreduction of carbonyl compounds, which is common in aromatic ketones. So carbonyl compounds both on direct photolysis as well as on the indirect photolysis undergo photoreduction to give undergo reduction of carbonyl and also the dimerization to give a diol derivative. Today we would like to discuss the 4th type of reaction, that is photoaddition of carbonyl compound to alkene, is known as patterno-buchi reaction. These reactions have been studied extensively, and a lot of examples have been reported. Few of them will be discussing in this lecture. See, photoaddition of carbonyl compounds to alkene to generate 4-membered oxetane ring was first discovered by patterno-buchi reaction. First discovered by patterno-buchi, and it was later on re-investigated by Buchi and co-workers, and now at present these reactions are reported as patterno-buchi reaction. A variety of such reactions have been studied and several examples are reported in the literature, and it is assumed that the reaction proceeds via the attack of excited carbonyl to alkene derivative to generate more stable 1,4 diradical, and the reaction is regioselective because out of the formation of two products, one product is formed in major amount because of the stability of carbon center radical. So if we the overall so say for example, as a representing example, the addition can be represented by this is the carbonyl compound adds to alkene, and you can see this alkene is dimethyl substituted ethylene and is unsymmetrical alkene, and in the presence of light carbonyl goes to an excited state. Excited state can act to one of the carbon to generate a radical here. So this is or it can also might attack on this carbon to generate a radical here. So these two carbon center radicals are, of course this is common in both, so this is not the deciding factor. So this the carbon center radical is going to decide the stability, and here you can say that this is the tertiary radical, this is a primary radical, and we know that the stability of radical lies in the order tertiary is more stable than primary, and this combines to give this as the major product and this as a minor product. So we can say that this reaction is selective in the sense that the more stable radical is formed preferentially as compared to less stable radical, and hence this more stable radical leads to the formation of a 4-membered oxetane ring. So 4-membered oxygen containing heterocycle, so known as oxetane. So oxetane ring formation takes place in this type of reaction, and which is we referred as the patterno-buchi reaction. As I have mentioned that this reaction is regioselective because it gives the more stable carbon centered radical, and hence several examples have been reported, and few examples are shown over here. Say for example, this is another this is a benzophenone reacts with the alkene. This is a methyl group, and then this is a cyclopropyl group. So in the presence of light, carbon goes to an excited state. this excited can add to this carbon to generate this is a second, tertiary radical. There is a methyl group here, CH3. So this is a tertiary radical. There is also possibility that this excited carbon can add to this to give a less stable CH2 radical. This is a primary radical, and then we have a CH3 and then a cyclopropane. This is a so this is another possible attack of the carbonyl to give a primary radical. This is less stable, whereas the preferential attack of excited carbonyl takes place to CH2 groups to give a more stable carbon center radical. This might combine to this this radical to give a this product, or since this radical is adjacent to the cyclopropane ring, there is a possibility of opening of the cyclopropane ring to give a this carbon center radical with the ene formation, and then this can once again couple to give how many rings? So 1, 2, 3, 4, 5, 6, 7. 7-member ring system is formed. So ring expansion product is observed in this particular case, where the excited carbonyl adds to this unsymmetrical alkene to give a more stable tertiary radical. This tertiary radical is adjacent to the cyclopropane ring. The opening of the cyclopropane ring may take place with the generation of a new carbon center radical, or it can even combine. So two products, and this is more susceptible to give this product, because this is again is a ring stain system, a 4-membered ring, and there is a 3-membered ring and the 2 phenyl groups, and so on and so forth. But still both this will be a minor product and this is a major product. The main step involved is the excited carbonyl leading to the more stable carbon center. It is a primary step where the photon is required, and then rest of the reaction is just a radical coupling and radical transformation to give this desired product. This is another example of a reaction of a carbonyl compound to alkene. This is, of course, this is not a simple alkene, this is alene, and then in the presence of light, this excited carbonyl can add to either this carbon to generate a radical So this is a radical adjacent to on the double bond, radical on the double bond, and we have already seen in the case of Norris type 1 of alicyclic ketone, the radical on the double bond is unstable, so it doesn't form, but this carbonyl adds to this excited carbonyl adds to this carbon to generate a radical. This is a tertiary radical, and then this is the preferential attack of excited carbonyl to the alene carbon, sp hybridized carbon, to generate this radical, and then of course this radical is tertiary as well as is stabilized by the adjacent double bond. So this may also get stabilized with the presence of a double bond, and then this can combine to give this as one of the major product in this particular cycloaddition of carbonyl to alene reaction. So you can see that the reaction is this stereo selective, in the sense that although there is a possibility of two products, we get one product exclusively or in major amount. And of course this is ruled out because this radical is generated on the double bond, and we know that the radical on the double bond is unstable and it doesn't form, and then other possibility takes place. This is an example of an intramolecular of addition of carbonyl to alkene. Intramolecular, in the presence of light, you have a double bond here, carbonyl in the same molecules. Intramolecular photocycloaddition, photoaddition of carbonyl to alkene takes place, and here you can see that in the presence of light, excited carbonyl can add to this to generate a radical here, or there is another possibility of this excited carbonyl might add to this. So if we add this one, so get a primary radical here. A primary radical here, we are going to get of course there is a methyl group here, CH3. So methyl group here. So it is a tertiary radical and also a 6-membered ring formation. Here we are going to get a 5-membered ring with 2 oxygen atom, and also it is a primary radical. So it is not going to is a preferable attack. So preferable attack of this excited carbon in the presence of light is the excited carbonyl can add to this carbon. This is CH3 here. Excited carbonyl can add to this carbon to generate this radical, and this radical has 2 possibilities. You can recouple to give a 1, 2, 3, 4 ring system. Of course it is a unstable, but other possibility is it might open up. This can open like this to give it this in ketone, and of course after the rearrangement we have a here we have R here. Of course there are some, so R, CH3, these 2 are missing in the starting material. So there is an R here, and then we can have a R as well in this one. And so this is an example of an intramolecular photoaddition of carbonyl to alkene. Both carbonyl functionality as well as double bond is present in the same moiety. So under photolytic condition, excited carbonyl can add to the double bond, and of course it will be a preferential attack to just see that which radical is going to be more stable, and hence it gives a tertiary radical as a stable radical, and then it might once again couple a radical coupling to give a this product. Of course is under highly strained ring system, and then the yield will be very, very low, and the fragmentation is going to be a major route for this, because there is a radical adjacent to the carbonyl, and then this might lead to the another product. So these are a few examples of patterno-buchi reactions, addition of a carbonyl to alkene. The reaction is the first step is the attack of excited carbonyl to alkene to generate more stable carbon center radical, and then this 1,4 diradical might recombine to give a 4-membered oxygen containing heterocycle known as oxetane. So these are few examples. Many more examples have been reported in this reaction. Here is another example. Here the benzoquinone reacts with cyclooctatetraene under photolytic condition. Here as well excited carbonyl can add to one of the double bond. Of course here it is all are symmetrical, so any excited carbonyl might add to any of the double bond to generate a 1,4 radical. 1, 2, 3, 4. 1,4 radical is formed after the attack of the excited carbonyl to one of the double bond of cyclooctatetraene. Benzoquinone to cyclooctatetraene. Cyclooctatetraene. So this will, and here you see people have just made an attempt to trap this 1,4 diradical just to see that the reaction proceeds via 1,4 diradical. So this 1,4 diradical was trapped by oxygen. So under oxygen atmosphere, this 1,4 diradical can add to oxygen to give a peroxide derived products, and then this is a evidence that the reaction proceeds via the attack of the excited carbonyl to double bond to generate 1,4 diradical, which can nightly react with oxygen and then to give a this peroxy derived product. So this is the evidence that the addition of a carbonyl compound to alkene, the first step is the excited carbonyl adds to double bond to generate 1,4 diradical, which once again undergo radical coupling to give this product. So here it is people have tried to see the mechanistic aspect to see that really this reaction is proceeding via 1,4 diradical or not, and they have trapped this with oxygen, and then this is the formation of this radical very the concludes that the proceeds this reaction attack of the carbonyl to alkene proceed via generation of a 1,4 diradical, which may undergo further reaction to give different products. The addition of the carbonyl to ring stain system has also been reported. Of course, what we have seen so far is the addition of carbonyl to alkene, but these reactions have this is a quadricycline reaction of carbonyl to quadricycline has also been reported because it's a highly strained system. It opens up very fast under catalytic under photolytic condition, and then the excited carbonyl on reaction with under photolytic condition on reaction with quadricycline, the excited carbonyl attacks on the exosite of this quadricycline to generate a 1, 2, 3, 1, 4 this radical. It opens up 1, 2, 3 1, 2, 3 and 4. This opens up this this bond opens up to give a 1, 4 the diradical species, and this diradical species which is formed has the possibility to further ring opening reaction takes place. This radical can form a double bond here, so there is a possibility of opening of this bond A, or there is a possibility of opening of this bond B with the formation of a double bond here. So when bond A opens up, then we get a new carbon center radical here, and then this can combine to give this as one of the products. Whereas if bond B, cleavage of B bonds takes place, then we get a new carbon center radical, and then this can combine to give these two products. So this product number 1 and product number 2 has been reported on reaction of carbonyl compound with quadricycline, highly ring strain system, and then it attacks on from the exosite to generate a carbon center radical. This carbon center radical can further one of the cyclopropane ring can open. There is a two possibility of opening of cyclopropane ring to double bond and then this radical, or this double bond and this radical to give these two derived products. So so not only the carbonyl compounds add to double bond, but it can also has been reported to add to a highly ring strain system, and which is susceptible to undergo opening up under very fast conditions. So this also reaction is reported under photolytic condition, reaction of a carbonyl to quadricycline to give two products as shown over here. Another important aspect in the patterno-buchi reaction is the stereochemistry of the product, because what is this? Say for example, we have a carbonyl. We have a carbonyl, say for example CH3, or we have a cis alkene, say R and R. So this under photolytic condition has been reported to give R and R. Now this is a cis alkene, and then now what is the stereochemistry of this alkene in the product? This is oxetane product which is formed under photolytic condition of on reaction of carbonyl to alkene. So in order what is the stereochemistry is a extremely important aspect to discuss here. And if we start with transalkene, so for example, we have instead of cis, we have a transalkene plus R under photolytic condition, CH3. Now this say stereochemistry is going to be retained in the product, as we start with R. Transalkene is retained in the product, or start with cisalkene is going to again retain in the product or not. This is a important aspect which has been discussed. Before discussing this, it has the reaction of this stereochemistry of the retention or inversion in the inversion of stereochemistry in the product oxetane formation depends upon the what type of substituents R is, whether it is an electron donating group or it is an electron withdrawing group. So this the nature of the substituent, whether R is an electron donating like methyl, ethyl, propyl and so on, or electron withdrawing like cyano and so on and so forth. So this plays an important role. The nature of this substituent in the alkene, what type of these substituents are, whether it is a electron donating group or electron withdrawing group, and this nature, electron donating or electron withdrawing group, presence of a methyl group and electron donating, presence of an electron withdrawing group like cyano, is going to decide the stereochemistry of the product in oxetane formation, whether the stereochemistry is going to retain or is going to change in the product formation. So this we are going to discuss in the next lecture, because before going to this we need to discuss the homo-LUMO of the alkene, unsubstituted alkene, and as well as the substituted alkene containing electron donating group or electron withdrawing group. So what effect on the energy of the homo-LUMO is going to take place, whether how is going to affect on the nature of the substituent, whether it is a donating group or withdrawing group. So this we are going to discuss in more detail on the next lecture. Thank you very much.